Okay, this one will do problem 670 in Hibbeler. So this is a beam bending problem. It's a stress analysis type problem. It's not really a design problem. Everything's given to you here. You have this truss, well, really a composite beam if you consider it here. And this is the cross section of it. So it's a larger, it's two tubes connected by this wire brace through the middle. And the problem basically tells you can ignore the effect of the web, in the sense that the web doesn't really add any considerable stiffness or doesn't carry any significant load because it's very small. If you look at the eye, if you were to consider it, it would be a minor increase in the eye of the whole thing. Really, we just want to consider that the load is carried by the geometry of the upper hollow tube and then this lower solid tube. Here's the loading of the beam, all right? And you have to figure out the max bending stress. So again, the first thing we're going to do is get the bending moment diagrams. Or basically we need that to figure out where the max bending moment is. All right. Once we know the max bending moment, we're going to have to do the flexure formula to compute the stresses. But before we'll do that, since we have this kind of composite section, we'll have to do the analysis on the cross section, composite cross section. All right. To get this is basically to get the location of the neutral axis or the centroid, and to get I. And then finally, once we know those things, we can put those into the flexure formula and get that the bending stress is that max moment times the C, which is, the C to the outermost C, or which fiber is the outermost from the neutral axis, because that's where the max stress will be, over the I. All right? So I actually should say, in this one, we also need to get the two C's. C, the distance from the neutral axis to the top, and the distance from the neutral axis to the bottom. And actually in this one, as is typically the case when you have a bigger geometry on one side, the neutral axis will be shifted up. And so actually the farthest fiber will be down here, and the max stress will be down here. So those are the steps we're going to take. All right. So let's do the bending moment diagram first. All right. So again, really, you need to figure out where the maximum bending moment is. The cross-section is uniform, so wherever the max bending moment is, that's going to be the section where you'll have the maximum stress. If you had a beam that varied in cross-section, where the cross-section changed, or materials changed, usually it's a cross-sectional change, then you would have to check for the max stress in each one of those sections. So you'd have to look for the max moment in each one of those different sections. Okay. All right. So this part has symmetry again. This planar view is symmetric. So let me put right through the middle point the axes. It's supposed to be right in the middle of the beam. This will be the y direction, and that'll be the x direction. Okay. So first, we're going to analyze the bending moment diagram in this 6-foot section. So I'll have to take a cross section there, and I'll consider this right-hand side. And then we'll have to look at where this middle 6-foot section, where the distributed load pops up. Okay? All right. So I need to get the reaction forces on this. You can do it through sum of forces and sum of moments. This is a statically determinate problem, right? We have two reaction forces here. We'll just call them R. You're going to find out, obviously, that they're equal because of the symmetry of the problem, all right? But you could, if you don't believe it, give them different values and go through sum of forces and sum of moments, and you'll see they're equal. But it has to be such that 2 times R, right, has to equal the 100 pound-foot distributed over this 6 feet. All right, so the feet cancel out. So that gives me that R has to equal 2 divided by, so it's 300 pounds. So each one of these is 300 pounds acting upwards. Okay? All right. So now let's first look at this section. So this is going to be the bending moment diagram from X between 3 feet and 9 feet, right? Because this distance here is 3 feet, and then this distance here is 9 feet. Okay? All right. So the free body diagram there is basically just going to look like this. Here's the upward 300-pound force. Now this is a negative X face, so the positive sense for the moment is going to be clockwise. This distance here is X, so that means that this distance here has to be 9 feet minus X. So I probably will convert everything to inches. So 12 times 9 feet. Let's just do it now. This is 108 inches. So this is 108 inches, and then 3 feet. I can do that in my head at least. That's 36 inches. Okay? So let's do everything in inches so I don't have to worry about units. All right. Of course, the shear force, the positive sense would be upwards, but we're not worrying about shear in this section, so there it is. So if we do sum of moments around this point here, we get the internal reaction moment, which is a negative moment, is balanced by the positive moment of the 300 pounds. So that's 300 pounds, and its moment arm is this 108 inches minus X. So now X is going to be in inches. All right? Okay. So it's linear. At the end, the moment vanishes. And that's always going to be the case unless you have a built-in support or some externally applied moment. All right? And then what happens here is the slope. So I'm going to do this. Okay, so the moment here at 108 is 0. And then it has a negative slope of negative 300. So I'm just going to be increasing. Where the slope here is 300 pounds per inch. Okay? So that's the moment. I guess we should get it at 36 inches. That's the point where we switch over to having the effect of the distributed load. And if we do that, the moment there is going to be 108, enter 30, oops, I keep saying 30, 36 minus times 300. So that at this point here, the bending moment is 21.6 pound inches, or 21.6 kip inches, all right? All right, so now we need to do the bending moment between 0 and 3 feet, or 36 inches, right? That's 3 feet. So between this point and this point. Now when we do that, we're still going to have this same moment actually from the 300 pounds. That's going to be the same. And this distance here is still going to be 108 minus X. And this distance here is still X. Here's the moment. And the shear force, I won't draw the shear force. But we also are going to have the downward distributed load. Now this distributed load is going to start here. This distance is 36 inches, okay? And so this distance is 36 minus x. All right? Now, we can make this a little simpler. We can figure out the effective force of this, right? Since it's uniformly distributed, we can replace that effective force with a concentrated force at the midpoint. All right? This is going to have a value of 100 pound-feet, and it's distributed over this, well, okay. So I gotta be careful about units here. It's distributed over this 36 times x, but I should, see, I have the feet down here in the units, so I should probably not use the 100 pound-feet, but really 100 divided by 12 to get it in pound-inches, right? So now that's 8.33 pounds per inch, right? That's this distributed load. This is divided by 12, 8.33 pounds per inch. Why do I have to do that? Well, my distance that's applied over here is going to be in inches, right? I'm keeping everything in inches, so I have to shift this distributed load from pounds feet to pound inches. So we got 36 inches minus x. That's the magnitude of the force. And this distance, which is going to be the moment arm, here is half of this distance. So that's 36 inches minus x over 2, right? So that's the effective point force for that distributed force. So always remember, you have, when you're doing these, you have to use the distance that it's applied over. Don't use the full 3 feet. That's going to be incorrect. As you move an x, we have more distributed force. So this vector not only moves up, increases, it actually is going to shift a little bit, right? Because its centroid is going to move over, okay? So it's very important. Make sure you use the right distance for the distributed load, not the total distance, right? This has to be at some arbitrary point x to get the moment at some arbitrary point x. Okay, so now we can do the sum. Okay, so again, we got m of x, right? That's a negative, so we'll put that at the left-hand side. And then we have this one, which is a positive. That's still the same. 300 times 108 minus x. That still exists. But now we have this additional one, which is going to have a negative moment, and its value is going to be 8.33 times 36 minus x. That's the magnitude, and its moment arm is 36 minus x on 2. So this is going to be squared on 2. All right? So basically it's the same thing we had before, plus this little quadratic. Okay? So if we were to plot that out, let's see. Let's try to sketch it. So here is 3 feet. This would be 6 feet. This would be about 9 feet. Okay? So on this distance here, we have the, it's supposed to be a straight line, and it would continue up in that manner, except we have to add on to it this, or subtract off it this quadratic. So this quadratic let's do it at x equal to 0. You know, at this point, this moment has 0, and then at x equal to 0, the value is going to be, let's just figure this out. Let's figure out the whole thing at x equal to 0. So the moment at 0 is going to equal 300 times 108, okay, this term, and then I get a minus 8.33 to divide, and this is going to go to 0, so just 36 squared times, and then that's going to be a minus, so still positive value, it's going to drop down to a positive value. Let me just double check that, but I think it drops down to a positive value of 27,000 pound inches. Okay, so it's 2,700 pound inches. So it's still going up. I mean, that seems a bit odd. Let me just double check the numbers. Okay, it's 3420. Yeah, no, that's right. So, and I also know that because of symmetry, the moment, well, whenever you have these sort of symmetry conditions, the moment has to be at a stationary point. So it has to have this inflection, it has to have the slope of 0 there. So what's probably happening is this is value of 21.6, and then it goes up a little bit to 27. So I guess it looks like this. So it has a little curve to it. And this value here goes to 27. So that's the maximum, right at the center. That's where we have the maximum moment. Here we have the moment, the max, and it's equal to 2,700 pound inches. Okay? So that's the point where we're going to get the maximum stress. All right? So now we know that. Now we have to do the analysis on the beam. Okay? So we need to get the second step. Now we have to do the geometric analysis. Okay, so we need to know the location of the neutral axis and I. We need to know to get the right C's and I to apply the flexure formula. That's actually the easiest part, the MC over I calculation, right? Okay, so let's make a little bigger picture. So we have the section we're looking at is as follows. Solid on the bottom, and then the top circle is hollow, and it has a outer diameter of 1 inch, and then an inner diameter of 3/16 of an inch. Wow, so that's pretty thick. I didn't quite draw it to scale. It's actually a lot thicker than that. And this one is solid, and it just has a diameter of 1/2 of an inch. And this distance between the bottom of this circle and the top of this circle is the 5 3/4 inches. All right, so let's pick our datum that we're going to get the location of the neutral axis, bottom of this circle. All right. So to get the location of the neutral axis, right, we need to get the centroid. Here's that centroid location. We want to compute this distance, and we're going to call that YC. That's the location of the centroid of the composite body, right? I don't know where that is. But YC is going to equal, and let's call this body 1, and this is going to be body 2. So the location of the centroid is going to be the area of body 1 times the distance from the bottom to its centroid plus the area of body 2 times the distance from the reference to its centroid over the total area. All right? So let's kind of tabulate those. The area of the first one is going to be the diameter squared over 4 times pi. So it's just going to be pi on 4, 1/2 squared, right? So that's 1/4. So that's pi over 16, which is 0.196 inches squared. The distance from this low reference to its center is geometric center is half the diameter or the radius. So that's going to be 0.25 inches. Okay, right. That's just this distance. That's y1. This distance here is what I'm calling y2, distance from the reference to the center, geometric center of the second body. So the area of the second body is pi on 4, 1 squared minus 3/16 squared. And that comes out to be 0.758 inches squared. And its location of its centroid is this distance, the diameter, which is 1/2, plus 5.75, plus half this distance, so that's the, plus another half. So that's 6.75 inches, okay? So now that gives me that YC is going to be 0.196 inches squared times y1, which is 0.25, plus the second area, 0.758 inches squared. Its centroidal distance, 0.675, over the total area, 0.196 plus 0.758. So this is inches squared times inches, that's inches cubed. This is inches squared, so we're left with just inches, and the value is going to be 5.42 inches. So this distance here is 5.42 inches. Okay? So that means that this distance here from the neutral axis to this lower outer fiber is 5.24, and this distance to this outer fiber here, that would be the second C, right? This is actually the same as like C1 and C2. Distance from the neutral axis to this outer fiber would be, let's figure that out. That's going to be, well, this distance here is 6.25 minus that, right? 6.25 minus. So this distance here is going to be 0.834, and then we're going to add on to that another inch for this diameter, so that's going to be 1.834. So those are our two C's. So obviously the greater C is down to this point, so this is where we're going to have the max bending stress. Right at that point, okay? Okay, well, now we need to compute the I. So the I, we have to use the parallel axis theorem. So for the I, for the total section, is going to be the I of the first section plus the I of the second section. These are the I's about the neutral axis, right? So this one is equal to the I of that first section around its centroid plus
the shift from parallel axis here. So that's the area of that. I should do this one times its distance from the neutral axis. So that's, we need this distance, the distance from the neutral axis to the centroid of body 1, right? This is the I about the centroid, and we need this distance. So that's going to be 5.24 minus this half height, or minus the quarter. So that's 5.17, I think. Let me just do that. Yeah, 5.17, right? It's 5.17 inches. And it's actually technically a negative 5.17, but we're going to square it so it really doesn't matter. I'll just put the negative sign in there so that you know sign does matter for this one, right? Remember always. Sign, not sing. Sign. Okay? And then this one is going to be equal to its I around its centroid plus its cross-sectional area times this distance. The distance from the neutral axis to its centroid, which is going to be the C minus half the diameter, right? So it's 1.834 minus this half diameter, the diameter is 1, so it's minus a half of an inch. So that's 1.334 inches. That's the distance we want there. 1.334 squared. Okay, we already know the A's. We just need to get the I. So this one here, well, let's do I1 just to be consistent. I1 is going to be the pi over 64 times its diameter cubed, diameter to the 4th. So that's 1/2 to the 4th. And so that gives me 3.07 inches to the 4th. This area here we already computed to be the 0.196. So this total number here becomes, I'm sorry, I got this wrong. This is 10 to the minus third. Okay, I left the minus third off of there. That's going to be important, obviously. So this gives me 3.07 times 10 to the minus third plus the area, which is 0.196. Enter. And its distance, the 5.17 squared times. So this value here, you can see, is 5.23. So it dominates this. So basically, the I, this almost acts like a point mass at this, at that point, or area point at that. This has minimal consequence. It's all, the I is all garnered from the fact that this is set off so far from the neutral axis. So anyway, this becomes 5.24 inches to the 4th. Likewise, this one is going to be pi over 64, the outer diameter to the 4th minus the inner diameter to the 4th. So that's going to be, let's clear all this garbage out of here. This becomes 0.0490 inches to the 4th. And again, this is going to be dominated by the offset, right? So this actual I is not that much, but the I, when you offset it, is going to become much bigger. So this becomes 1.334 334 squared. Add that, so this becomes, this term here is 1.35. We add that to the 0.05 and we get 1.40 inches to the fourth. So the total I is this number plus this number. So the total I is 1.4 plus 5.24, or 6.64 inches to the fourth. So you can see, you know, these bodies by themselves have very small eyes, right? But when you space them off this distance, you can see the eye of the total section goes up 1, 2, 3 orders of magnitude, okay? So it has a significant effect. So again, if nothing else, you know, sometimes you can forget the details of doing these calculations. Maybe you can always go back in your books later in your career, but you always have to have ingrained in your psyche the fact that by distributing mass or area farther away from the neutral axis is a more effective design for stiffening and stress reduction of a beam. Okay, so that's the second part. Now we're pretty much done. We can do the third part. This is the easy part. So the max bending is going to be MC over I, where M is the maximum bending moment that occurs right at the midpoint, 27. So that's the 2,700 pound-inches. The maximum C, in this case, it's going to be the distance to this outer fiber, right? This one. That's the 5.42 inches. Okay? And then, I should actually, to be correct, we should have the minus on it, right? Really, remember the sigma is minus MC over I, where if we keep care on the sign convention of the bending moment, which we did, it'll tell us that, in fact, we get a compressional stress here and a tensional stress here, which I think is something weird about that. I think I did something wrong with that. I got to recompute that bending moment. So, and then over I is 6.64 inches to the fourth. So this gives me, yeah, I think there's something weird about this. I have a side change. I think I made a mistake in the bending moment diagram. Something tells me this is wrong, because I would have expected this to drop down. I'll just work this out, and then if there's a correction, I'll post the correction in text underneath the YouTube video, okay? 5.42 times swap 5. Okay, so this is telling me right now minus 22,046 PSI is the bending stress. Yeah, I think something's wrong here. What? I think actually, I suspect that this value might not be right. Okay? I think I might have made an error in this first step. But according, assuming I didn't, this is telling me that occurs right here. And it seems odd because it's telling me it's in compression, which I'm pretty sure is not the case. And this bending moment diagram looks odd. I would actually expect that this bending moment diagram would then drop down like this, okay, and give me a negative stress there. But I have a suspicion that it should actually do this. Let me check that. I'll stop the video now and see where my error is. All right, I double checked the values. Actually, it's not the issue that. This is a good point. It's too early in the morning for me. This number is correct. Okay, the 27 is fine. I double checked it. The problem here is that when we get worried about the sign convention on here, this C is actually in the negative y direction, right? So this is really minus 5.42. So we should have a minus sign here, which makes that a positive. Okay? So that means we have a tensional or extensional axial stress here
of 2,200 kips.
At this point, we would have, it's not asking this, but we'll just figure it out. It would be, the stress at this point would be minus 2,700 times its C, which is a positive 1.834 inches, the distance from the neutral axis to the outer fiber there, over I, which is still 6.64 inches.
And that turns out to be
a minus 7,460 psi. Okay, so we got compression stress in here.
it's much less than the extensional stress on the bottom. Okay?
So interesting to note here is by doing this and putting a smaller area and shifting it so that we have this imbalance in I, so we have a non-symmetrical cross-section, you're able to control whether the maximum stress will be in the tension or the compressional side, okay? So if you flip this cross-section upside down, if we flipped it upside down so actually that it looked like this,
So that the smaller rod was on top and then the hollow tube was on the bottom,
you would actually get the same values of stresses, okay? If we flipped it this way, the C's would be the same, other than the sign would change. The M would be the same, the I would be the same. But what you would find here is you would get the max stress up here. You get the max stress up here, and it would be minus 22,046 in compression. Down here, it would still be in tension, but it would be the lower stress of the 7,460. Okay?
oops. So, this isn't required, but again, we should always be thinking about these concepts of how to design using the physics that we're learning in this mechanics of materials class.
Ultimately, as engineers,
We design, right? That's our value. Not churning through these equations, but you have to. So the first step is to understand the equations, how to apply them, but really, hopefully before you graduate, you have a deeper understanding of the mechanics here, the physics, so that you can use these things to help actually design, right? So, this is obviously steel, but if you had a concrete structure, right, where it can support much higher loads in compression than in tension,
you would actually prefer a geometry like this.
okay? Still have the same maximum stress, absolute value, but we've designed this such that it's in compression, okay, as opposed to tension, all right? Okay, thanks. Sorry for the confusion on the C's, okay, but that's an important point.